Good afternoon to all of you.
Good afternoon, sir.
Good afternoon. Yesterday we were discussing, we defined the lower limit topology. So, that is the topology which is generated by this particular subsets of X. So, this B is a basis, so that we have verified uh, in these two conditions. And then we have seen that the topology generated by this basis is known as the lower limit topology. So that is nothing but the union, all unions of this type of sets, closed open intervals, and in particular this set is opening because it is union of two closed open intervals. It is open set, open subset of R. This is anyway subset of R. This whole set is a subset of R, which is open with respect to the topology generated by this basis, because it is union of two such closed open intervals. But on the other hand, we know that this is not open set with respect to real analysis. So that means the topology generated by open intervals, with respect to that topology, this is not open set. So therefore, it does not belong to the standard topology on R. So this is the last lecture, and I have given some exercises. So the question was that this X set, what is this set? So this is a general set. X can be R also, X can be the set of natural number also, whatever. These are the special example, but in this exercise, X is any general set. So over the general set X, which is any non-empty set basically, and over that set, whether this set T infinity defines topology or not. So that means whether T infinity satisfies the three axioms of the topology. So phi belongs to tau infinity, X belongs to tau infinity, that is already given. So first condition anyway it satisfies, but whether it satisfies the second and third condition, which is whether this family of subsets of X, so this all U's are subset of X. So whether T infinity satisfies is closed under finite intersection, whether T infinity is closed under arbitrary union. So that is what we need to check in this exercise. So I hope this question is clear. So what is the difference is that instead of the complement is finite set, here we are taking the complement is infinite. So the definition we modified from the finite complement topology. And one more exercise which I could not write yesterday, I was in a little bit hurry. So the last exercise which I wanted to give is consider the following topologies on R: tau 1, tau 2, tau 3, tau 4 and tau 5. So tau 1 is the standard topology, which we already know. Tau 3 is finite complement topology. Tau 2 is K topology, which I have given the definition yesterday in the one of the exercise. Tau 4 is this topology generated by the basis, which is intervals open A to closed B, right? And the final set which I am giving is tau 5, which is a topology having all sets minus infinity to A. So basically what we are taking is, I have a real line on which I am fixing some point A. This A may be positive, negative, 0 also. So in this set, what elements will be there? All the points which are left side of this A, x less than a. Right, so that is basically an open interval of infinite length, and we are actually excluding the point a because we are taking x less than a. So x is a real number such that x is less than a. So all these open intervals, first thing we have to check is it forms the basis, so it satisfies both the condition of the basis, and then once it becomes the basis we verify that the topology generated by the basis we will denote by tau 5. So these 5 topologies are given on the same set x equal to r, and on this real line we have to compare all these 5 topologies. So basically which topology contains the other, so that we need to check. So this is one of the good exercise in topology, so that we can understand the concept of basis, the concept of comparison of topology using the basis elements. So this is regarding the exercises. So let me start today lecture.
Sir, in the last lecture, you told that RL is that strictly finer than standard topology.
Yes.
So in the end, you also used something you were telling about the converts. Sir. Can you please repeat that?
Yeah, converge means we have to show the, yeah, so this is exactly the thing. So converge is not true, so that means this statement is false, right? So suppose this statement is correct. So if this is correct,
So
that,
here it should be RL. RL is contained in R, I think.
oh, so maybe I have written the inclusion in the other way. So now is it okay?
Yes, sir. Yes, sir.
Okay, so maybe I have written it's kind of typo. But did you understand this thing?
Yes, sir. Yes.
That if I take 1 belongs to the closed open interval 1 to 2, then I cannot find the open interval which contains 1 and it is contained in the closed 1 comma 2.
Yes.
Right?
Sir, can you repeat that K topology definition again?
Yeah, so where is that? This is, yeah. Okay, so we already know if I have a basis, then I can generate the topology. This is the union of the basis elements, right?
Yes, sir.
Yeah, so here the this topology, K topology, is what it is generated by this family. This family is a subset of X, collection of subsets of X, and in this thing what we are saying is first of all B is a basis. So what is this B? B usually in standard topology, what is the basis? This is a collection of open intervals, right? So in this new basis, so usually we denote the basis by B. So every time I'm writing B, but this B is basically changing because here B is this. In standard topology, B is only this set, right? So basically we are adding these more sets in the collection of the open intervals. So what are these sets? These sets are, for example, if I take so what is, let us say 2 3 minus k. What is this set? K is basically 1 upon n sequence, you can say. uh, so 1 1 by 2 1 by 3 1 by 4, and z plus usually we take is n union 0. but since we are taking 1 upon n, we are not I think including 0 here, otherwise it will be kind of infinity. So z plus means for simplicity let us say it is set of natural number only in this example. So what will be 2 by 3 minus k? What is this set? So we know that if I have sets a and b, what is the difference of set? What is definition of a minus b?
Sir, it is all the elements of A which are not in B.
Which are not in b. So what are the elements of open interval 2 3 which are not in k? K is the set of elements. What is k? K is basically 1 1 by 2, this set.
So it will be 2 comma 3 only.
It will be whole interval, right? But now if I take 0 1 minus k, so that will be different set than open interval 0 1, right?
Yes, sir.
So that way I have taken all the such sets, and these sets I am adding in this collection of open intervals. So now I have more collection of elements of B than the standard basis on R. So now basically the set B of the I'm not only taking open intervals, I'm including basically these new sets which are other than open intervals, right? So they will add up here, and this whole connection B will generate, because it is different than the collection of all open intervals, it may generate some different topology on R, right? So for example, this set 0 1 minus k is open in this topology generated by B. In the topology generated by B. So now is it clear that this is different example than the usual standard topology?
Yes, sir. Yes, sir. Clear.
Yeah, so first thing we need to check that this B is a basis. So first condition is anyway clear because all open intervals are there. So you need to check the second condition of the basis, whether it is satisfied or not. So just try this example. Anyway, it is new for us.
Okay.
And you can take help of the books also. So did you understand what are these sets, right? So that means you understood basis,
Yes.
and now you have to verify these two properties. That is the exercise. So I hope question is clear.
Yes, sir.
Okay. So today I want to discuss. So there are some ways to construct new topologies by use of the earlier topologies. So before we go there, there is one question that if I have a vector space, I have a in vector space, is a basis unique in a vector space?
No, sir.
It is not unique. So do we know any example of a topology which has two different bases?
R.
R has two different bases. What is the what are the bases?
Trivial. We can also take that discrete also.
No. You're.
Okay, okay,
I'm not
okay, okay,
asking
okay.
different examples of topology. I'm asking
Topology, okay.
if I have
Basis.
a topology, then can I have two different bases which the topology generated by two different bases is the same topology.
R has open sets, open
Okay.
intervals.
Right. So R actually we discuss R as open intervals. That is correct. But the example which we discuss in some different space on R we did not compare two topologies which are same so far, if I remember. R and RL are different, right? Lower limit topology and R is standard topology on R is different. So that we verified. So
Yes, sir.
on R we don't know. What about other sets? Did we check any two bases which generate the same topology on a given set X?
Yes, sir. On the R2, we have rectangular and circular that could be
Yes, so
found.
that is on R2 we discuss. So one is the basis which contains all the circular regions,
Another
and
rectangular one.
on the other hand we have discussed all the rectangular
Rectangular.
regions. So these
Yes, sir.
both bases generate the same topology that we have verified. So that means for the topology also it can happen that the topology is same on a given set X, but it has two different bases. So like vector space also. Similarly, we have this notion here also. Such a thing can happen. Okay, so this is one thing I wanted to mention. Another thing is that in this regard is, so we have seen that all basis elements are open in the given topology. So that means when I consider the topology generated by rectangular regions in R2, then the interior of R2 is open with respect to rectangular region. With respect to the topology generated by rectangular regions. Okay, so since we are saying the topologies are same, so can I write this as this rectangular region as a union of circular regions, because we are saying it is also open in the other topology, right? Because we have basis is a subset of tau b,
Yes,
and we are
sir.
saying tau b is tau b dash. So that means b is contained in tau b dash, as well as on the other way around b dash is contained in tau b. So all rectangular regions are open with respect to the topology generated by circular regions, as well as all circular regions are open with respect to the topology generated by rectangular regions. So since it is open, that means we can show this rectangular region, that means interior of this rectangle, as a union of circular regions, arbitrary union. So is it visible here how that I can fill any rectangular regions as a union of circular regions? So for example, if I take this circle, right? So inside this circle, whatever points are there in the first set b1, right? So then I can take another circle b2. So b1 union b2 will cover all these points. then I can take B3, which will cover all these points. So this way I can add as many sets I want to add as a circular regions, and I can always fill a rectangular region. So basically here we are showing that I can write a rectangular region as a union or arbitrary union of the circular regions. So that means it is open with respect to the topology generated by circular regions. Okay, so this is just a remark kind of thing. Okay, so today I want to discuss the subspace topology. So subspace topology means for vector space we have the notion of subspace. Methods to construct new topological spaces. So topological spaces means let tau be a topology on the set X. So if tau is the given topology on the set X, then we say that X along with tau is a topological space. So this is just a terminology we will use here. So if I don't want to write this long statement, I will just write that X tau is a topological space. So that means tau is a topology on X simply. So the definition of subspace topology. So if I have a vector space, I can find a subspace. Same way, if I have a topology on X, right? I could have also written X tau is a topology, but I have written tau is a topology on X. And let I take any subset of this set X, right? Y is a subset of X. Then I will define a family of subsets of Y as tau Y. So that is a U intersection Y, where U is element of tau. So is it clear that this is a subset of Y for every U? U belongs to tau. What is tau? Tau is a subset of our set of X. So that means U is a subset of X, right? So if U is a subset of X and I am taking U intersection Y, so is it clear that U intersection Y is a subset of Y?
Yes.
Yes, because A intersection B is always subset of B. It doesn't matter what is U. Okay, so this is a family of subset of Y. So the first thing we want to check is this is a topology on Y. It is not topology on X, it is topology on Y. So this topology is known as a subspace topology. So first thing we will first check whether it is a topology or not. So that means this proposition says that we have to check the three axioms of the topology. So what will be the first axiom in this case, because we are saying it is a topology on Y. So what we need to check in the first axiom?
Y and phi are belong to there.
Exactly. So instead of phi and X, we will check that phi and Y belongs to this family. So the first condition is to check phi comma Y belongs to tau Y. So what are the trivial elements of tau? We already know that tau is a topology on X. So the first axiom of tau will give us that phi and X belongs to tau. So that we will use here to prove phi and Y belongs to tau Y. So clearly phi and X belongs to tau because tau is a topology on X. So first property of topology on X says that phi X belongs to tau. Now if phi X belongs to tau, I will get two corresponding elements of tau Y when u equal to phi and u equal to X. So therefore phi, when I take u equal to phi, I will get phi intersection Y. This is the element of tau Y, and X intersection Y belongs to tau Y, because this is the way we define the family. This family contains the sets u intersection Y whenever u belongs to tau. So we know phi belongs to tau, so it will give phi intersection Y belongs to tau Y, and when I take u equal to X, I will get X intersection Y is element of tau Y. So now what are these sets? Phi intersection Y is nothing but phi. So phi belongs to tau Y because this is exactly this set. Same way, Y is a subset of X, so X intersection Y is Y. So Y also belongs to tau Y. So we check first property. Same way we will check the second property and the third property. So basically what we are using here is we are using the properties of topology on X to prove the corresponding property of Y. Right? So now to prove the second axiom is tau Y is closed under finite intersection. So we have to take n elements of tau Y. So what will be the n elements of tau Y? The elements of tau Y is of the form u intersection Y.
Intersection u1 intersection y u2.
Right, so in that way. So let us take n such elements. So let u1 intersection Y, u2 intersection Y, so on, un intersection Y are elements of tau Y. And what are u1, u2 belongs to?
Tau.
There are elements of tau. And tau is a topology. Right? So that is closed under finite intersection. So this will give intersection of u1, u2, un belongs to tau because tau is a topology. So now what can we say? Whether intersection of so can we write this in terms of intersection UK? Is it true?
Yes, it's true.
It is true, right? So you can take kind of A, B, C, D, 4 sets and verify this if you have any doubt. That A intersection B intersection C intersection D is yeah, but one of the sets should be same because here it is Y. Y is same in every intersection. So these two are the same sets from the set theory, and you can even verify using Venn diagram. And once this is true, so what we want to show, we want to show this belongs to tau y, and this belongs to tau y if I can write this set as a sum set of tau intersection y. So we are getting sum set intersection y. So is it belongs to tau? Yes, because
Yes, sir.
we have verified it here, right? Already verified.
Yes.
So therefore we have written the finite intersection as an element of tau intersection y. So therefore this is open. Open means it is element of tau y. So once again, we needed here to show these elements belongs to tau y, and in tau y we have only elements which are of this form, some set intersection y where this set belongs to tau, and that we have written in this form where the first set belongs to tau and intersection y. So therefore it is in tau y. Okay, so this is second property. Similarly, we can prove the third property. So third property is closed under arbitrary union. So again we will take u alpha intersection y where u alpha belongs to tau, right? Be an arbitrary family. So arbitrary means this alpha depends on any arbitrary index set, whatever we take. So what is the claim? Claim is that union u alpha intersection y belongs to tau y. So again, as you have already guessed that we will be using third property of tau. So since u alpha belongs to tau for all alpha and tau is a topology, therefore union u alpha is in tau, and therefore this we can write as union u alpha intersection y, right? And since this belongs to tau, this belongs to tau y. So simply using the so we have verified tau y satisfies 3 axioms of topology on y, so therefore tau y is a topology on y. So if I am given y is a subset of x, and I know all the elements of tau in x, I can find all the elements of tau y, where tau y is a topology on the subspace y, right? Using just this property that I know all the elements of tau y is of the form u intersection y, where u belongs to tau. So let us see some simple examples. first example is let us take if x tau is the discrete topology and let us take y is any subset of x. So usually here also we will assume that y is a non-empty set, right? Because empty set anyway we are not interesting. Empty set what we will do, and we cannot find continuous function because there is no element. So then what is tau y? So let me first write down what is tau y. Tau y by definition is u intersection y where u belongs to tau. So what is tau here? Tau is discrete topology on x. That means what? U belongs to
P of X.
P of x, power set of x, right? So what can we say about this set now?
Y. Y.
So
The entire Y.
how it is collection of sets, right? It cannot be the single set.
But sir, why is also collection of sets?
Pardon?
Why is also collection of sets? And it seems
Yeah,
can be
y
one.
belongs to tau y. That is correct. That is correct. Y belongs to tau y. Phi also belongs to tau y. What about the set? So as many elements in power set of x, as many elements I will get in tau y. It can happen that some of them the sets may be same. So okay, so let me simplify. So can I write it is power set of y?
Yes sir, हो जाएगा power set.
Right? So if you cannot not visualize, you can actually take kind of you can take x equal to 3 element set. You can y to be 2 element set and check whether tau y is power set of y or not. Right? For more clarity. If it is clear, then there is no issue. Right? So just verify tau y is p of y by taking this x and y. And on x we are taking discrete topology, so that means you will get 8 elements here in p of x. So this is first example. That means what is tau y? Therefore tau y is a discrete topology on y. So this says that if I take discrete topology on x, and if I take any subset of x, and if I define subspace topology, then the subspace topology is same as the discrete topology on the subset y. So that is meaning of first example. Now let us take some different kind of example. I'm not discussing trivial topology so that you can verify. So if tau is the standard topology on R, then on the integers are subset of R. the set of integers. So what is the subspace topology on Z? So that is, we denote it by tau y. Instead of tau y, we have tau z, because y is z. Right? Why we are taking z in this example? Because y is subset of R. So x is R in this example, y is z, because z is subset of x. So by definition, what is this? This is u intersection y. Y is z. U. So u is open in the standard topology. So that means u is open set in the sense of real analysis. What are the open sets examples in real analysis way? Open subsets
Open
of R,
intervals.
open intervals, arbitrary union of open
Union.
intervals, right? Open intervals and arbitrary union of open intervals. So open intervals are actually basic open intervals. So that is a basis in that example in the topology sense. So okay, what will be these elements? If I take U is open interval, so let us say open interval 1 to
Will be
4.
Z only.
Yeah. So what is the open interval 1 4 intersection Z?
There will be
3.
2, 3,
2 comma 3. Right.
3.
So
We
basically
are
what
getting
we are getting
subsets.
is a subsets of
Subset.
Z. Right.
Z.
So can I get all the subsets of Z in this way? Can I write all
Yes,
subsets
possible.
of
Yes,
Z
sir.
as
Yes,
a
sir.
open interval intersection Z? So that means Z is contained in this set, right? And is the other way is also true? If I take union of open intervals and I intersect with Z, it is always subset of Z.
Yes, yes.
That is also true. So these two
Sir,
sets
please
are.
pardon.
So yeah, so I have done some mistakes. So U intersection Z is always subset of Z. So that means
Yes, sir.
this is subset of power set of Z, right? This family is subset of power set of Z because each U
Yes, sir.
intersection Z is a subset of Z. Conversely, if I have any subset of Z, can I write A as a intersection of U intersection Z, where U is either open interval, U is a open set in R.
Yes, sir. It is possible.
It is possible, right? It is possible, right? Because if you want, you can take two intervals also as U,
Yes, sir.
union of two intervals. So that way we can write. So that means this is exactly power set of Z. So what is topology tau Z? It is power set of Z. That means it is on any set.
Discrete.
Yeah. So it is on X. If you have a topology power set of X, that means it is a discrete topology. So therefore, tau Z is the discrete topology on Z. So This is example where we are getting different topologies, because basically we are taking discrete set as a subset, so therefore we are getting discrete topology. So in some sense we can justify this. So before I stop, let me discuss a simple lemma in terms of the basis of the subspace. So if B is a basis for the topology on X, then the collection, so what we have taken elements of tau y as a u intersection y, where u belongs to tau, right? So the same way we will define basis on y as a b intersection y, where b is the basis element of the topology tau. So first we verified that corresponding to the open set in X, we are getting open set in Y as a U intersection Y. But now we have to correspond the basis elements also. So as many basis elements in the topology tau, as many basis elements I will found in the BY. So we want to verify that this is a basis. So basis, we have two conditions, right? So if you remember the definition of basis, we have for every x in X, for every x in X, there exists basis element which contains X, right? And if X is contained in V1 and V2, then there is B3 such that X is in B3 contained in V1 intersection V2. So these two properties we have for the elements of B, and that same two properties I want to verify for the elements BY. So let us verify in the same way. So we check the properties for BY using the properties, the corresponding properties for B as follows. So first property of basis BY is what? What we need to check?
X belongs to B intersection Y.
Yeah, but yeah. So if I take any element, not X, but since we are taking Y is a subset of X, right? We are checking for the subspace. So I have to take any element of capital Y, and then I have to find some element B intersection Y which contains that element, right? So let Y is any element in Y. So can I find a basis element which contains Y, because B is a basis and Y is a subset of X. So since Y is also in X and B is a basis, there exists basis element so that X belongs to B. Sorry, we are talking about Y. So Y belongs to B, right? Since Y belongs to X, there exists a basis element so that it contains Y. And since Y is in both capital Y and B, therefore Y belongs to B intersection Y. So here we are using first property of basis B. The same way, the second property we need to check, that is, if I have some element in two basis element, then I can find third basis element which contains first and second, right? So let me go there. Just a minute. Okay, so so what we need to show is we need to show if Y belongs to B1 intersection Y and Y belongs to B2 intersection Y, so where B1 B2 are elements of B, then there exists B3 intersection Y in By such that Y is in B3 intersection Y, which is contained in B1 intersection Y intersection B2 intersection Y. So again we will use to prove this, we will use the property of the basis B. So since I belongs to B1 intersection B2, where B1 B2 are elements of B, there exists basis element B3 such that Y is in B3 intersection subset B1 intersection B2. So now since Y is in both B1 and Y is also belongs to Y, so we can write Y belongs to B3 intersection Y, which is contained in so therefore we get this claim. We get the claim means we proved the claim. Okay, so the same way in the sense of open sets, we can also show that this is a basis. So now the two example which we discussed just now, so just try to find the basis elements of the subspace topology for this both example, right? Because we know what is the basis in discrete topology on X. What is the basis? The set of all singletons, right? And in this case the standard topology means B is the collection of all open intervals. Okay, so I have some power issue, so let me stop here.